If you've listened to this podcast for a while, you've probably heard me talk about a lot of different ways our climate is changing. We've talked about greenhouse gases, aerosols, heat waves, hurricanes, glaciers, El Niño, and feedback loops. But one question bubbles up after this. If scientists understand what's causing the planet to warm, why don't we just cool it back down? After all, if your house gets too warm, you just turn the thermostat down. Why couldn't we do the same thing for Earth? Believe it or not, scientists have been asking that question for decades. Some have even proposed a few ways to reflect a small amount of sunlight back into space in an effort to cool the planet. But a fascinating new study published just a few days ago reminds us that cooling the planet may be very different from controlling the climate. Because Earth's climate is a vast network of interconnected systems, each influencing the others in ways we are still trying to understand. So if we change one part of the climate system, what else changes with it? Welcome back to the podcast. I'm Dr. Mack, and this is the Climate Translation. When I first started teaching climate science, I noticed something interesting. Whenever we discussed global warming, someone would eventually raise their hand and ask a question. Dr. Mack, if we know the Earth's getting warmer, why don't we just cool it back down some way? I wish the answer I could provide was simple, but cooling something and controlling it are two different things altogether. Think about the human body for a moment. Imagine someone has a high fever. You certainly could lower the temperature by placing them in an ice bath. The temperature would drop. But have you cured the illness? Well, of course you haven't. You've treated one symptom. The underlying problem is probably still there. The Earth's climate works the same way. The average global temperature is only one measurement of a much larger system. Our climate is also made up of winds, ocean currents, clouds, rainfall, snowfall, sea ice, plants, animals, and countless interactions between them. Imagine walking into a room filled with hundreds of clocks. Every clock is connected to every other clock by tiny gears hidden inside the walls. Now imagine you reach over and adjust one clock with its hands. You might successfully change that one clock, but because they're all connected, you've just changed hundreds of others without even realizing it. That's what makes climate science so fascinating and so challenging. One of the biggest lessons we've learned over the last several decades is that Earth's climate isn't a collection of separate systems operating independently. It's one enormous interconnected system. The atmosphere influences the oceans. The oceans influence the atmosphere. Changes in sea ice affect sunlight. Changes in sunlight affect temperature, which affects evaporation, which affects clouds. And the clouds affect how much sunlight reaches the surface. Everything is connected to everything else. It's probably one reason you've heard me use the word system so often on this podcast, because that's how scientists increasingly think about our planet. In fact, Earth science programs in colleges and universities across the country are increasingly calling their introductory course Earth System Science for this very reason. We need to stop looking at it as though it has separate pieces. It's one connected machine. Now, scientists have developed some remarkably creative ideas for reducing global temperatures, and some of these ideas may actually work as intended. The real question isn't whether we can change one part of the system. Instead, it's what else changes at the same time. And that's exactly what a fascinating new study set out to investigate. It didn't set out to determine whether we could cool the Earth. Instead, it was interested in if the ways of cooling the Earth might produce different outcomes from what was intended. And as it turns out, the answer may be yes. So, how do you test an idea that involves changing the climate of our planet? Obviously, you don't, at least not in the real world. Instead, scientists use one of the most powerful tools that they have available: computer models. A climate model is really a giant physics experiment inside a computer. Researchers program the computer with what we know about physics: how the atmosphere moves and how oceans transport heat, how clouds form, and how sunlight interacts with the Earth. Then they ask an important question: what happens if we change just one thing? The computer can then simulate and give you some possible results. Now you might be asking yourself, how can scientists possibly know if what the computer spits out would actually occur in the real world? This is all hypothetical. We've never actually done it. And it's a good question. Before scientists can trust a climate model to explore the future, they have to ask a more important question. Can it accurately recreate the past and the present? Does it produce realistic El Niño and La Niña events? Does it reproduce the seasons? Does it simulate major ocean currents and jet streams? Does it simulate the rainfall patterns in the way we observe them today? So they set up a computer. They give it variables that we know describe how the climate was historically, and they run it and see what it comes up with. If what it produces is wrong, scientists go back and improve the model. If what comes up fits with what we actually have observed on the Earth, either in the past or now, then they can start asking what-if questions with much greater confidence. It's not perfect, because no computer model is, but it does allow scientists to safely explore ideas that would be impossible or irresponsible to test on the real Earth. In the study that came out from the University of California, Santa Barbara, researchers wanted to compare two different ideas for slightly reducing the amount of sunlight reaching the Earth's surface. First, they would spread tiny reflective particles high in the atmosphere, like what happens naturally after a large volcanic eruption. The second would work much lower in the atmosphere by making certain ocean clouds slightly brighter so they would reflect more sunlight back into space. Now, if I asked you before this study, if you had two different methods to lower the Earth's average temperature by about the same amount, would you expect the climate system to respond in the same way? Some of you might say yes. After all, cooler is cooler, right? But that's not what the researchers found. When they looked at only the global average temperature, the two results did appear to show similar results. Both cooled the planet. And if all you cared about was the number on a global thermometer, you might conclude that either approach would work equally well. But then scientists looked beyond the thermometer, and that's where things became interesting. Imagine you're a doctor performing annual physicals. You find two patients have exactly the same body temperature. Does that mean they're equally healthy? Of course not. One person might have a healthy heart. The other may have dangerously high blood pressure. Maybe one has a serious infection that hasn't changed their temperature yet. Body temperature is an important measurement, but it's only one measurement that matters. The climate system works the same way. Average global temperature tells us something important, but it doesn't tell us everything. Scientists also watch rainfall patterns, ocean circulations, and wind patterns, sea ice coverage, and ecosystems. And one of the most important natural climate cycles on Earth, El Niño La Niña. As we've discussed before on this podcast, El Niño isn't simply just a patch of unusually warm water in the Pacific Ocean, nor is its alter ego La Niña an unusually cool patch. It's part of a natural cycle that helps organize weather around much of the globe. It influences rainfall, storm tracks, droughts and floods, agriculture, and even hurricane activity. The cycle is one of the major ways our planet redistributes heat around the world. In these simulations, one cooling method left that cycle largely intact, the other weakened it substantially. Imagine you're trying to cool your house during the middle of the summer. You have two options. The first is to lower the thermostat by 2 degrees. Every room becomes just a little cooler, and the temperature changes evenly throughout the house. Now, imagine a second approach. Instead of adjusting a thermostat, you place a giant air conditioner in one room, but you make that room colder. Now warm air from the rest of the house starts flowing towards it. Doors create air currents and rooms warm and cool unevenly. Over time, eventually the air temperature in the house may end up about the same, but the way the air moves around the house has completely changed. It's similar to what the researchers found. The high-altitude reflecting method spread the effect relatively evenly across the globe, but the low-altitude cloud brightening method concentrated much of the cooling over one specific part of the Pacific Ocean, and that part happened to be just where one of the most important engines driving Earth's climate lies. As we've talked about before in this podcast, ENSO, the El Niño Southern Oscillation, which encompasses El Niño and La Niña, is related to how trade winds strengthen or weaken. Warm water shifts east or west across the Pacific, and the atmosphere and the ocean respond, back and forth, over and over again. The effects are felt far beyond the Pacific Ocean. The cycle helps determine where heavy rains are more likely to fall, where drought may develop, how jet streams bend, and how productive some fisheries can become. It can even influence hurricane activity from one ocean basin to another. It's one natural climate cycle with thousands of miles of influence, and it's why scientists pay such close attention to it. In this study, the researchers found that when cooling was concentrated over one sensitive region of the Pacific, the simulation showed a substantial weakening of that natural rhythm. In fact, in some cases, it reduced the natural variability of El Niño by 60%. That's a remarkable change. During many El Niño winters, the jet stream shifts southward across North America. That brings increased rain and snowpack to California and the American Southwest. That helps replenish reservoirs and provide water that communities rely on long after the winter is ended. If the behavior of El Niño changes, scientists would have to ask whether those familiar rainfall patterns would change as well. The same conditions exist across the Pacific. In South and Southeast Asia, seasonal monsoon rains are influenced by the complex interaction between the atmosphere and the Pacific Ocean, and those rains support agriculture for hundreds of millions of people. If one of the major climate systems helping organize those rainfall patterns changes, researchers naturally want to know what that would mean for people and ecosystems that depend on them. Everything I've talked about on this podcast, from sunlight to clouds to ocean temperatures to atmospheric circulation, it ultimately affects living things. Think back to something you probably learned in middle school science. Plants need sunlight. Without sunlight, photosynthesis slows down. The plants produce less energy, they grow more slowly, and of course they affect the entire food chain. The same principle applies to the oceans. The surface waters of our ocean are filled with tiny microscopic organisms called phytoplankton. Many people probably have never heard of them, yet they're the most important living organisms on the planet. They are the foundation of nearly every marine food web. Tiny animals eat the phytoplankton. Small fish eat those animals. Larger fish eat the smaller fish, and eventually the energy works its way up the system, from seabirds to marine mammals to us. In other words, tiny organisms support the entire ocean ecosystem. But they do something else just as important. Like the plants in your backyard, phytoplankton use sunlight to perform photosynthesis. It's an important part of Earth's carbon cycle, and it helps remove carbon dioxide from the atmosphere and move it to the ocean. So that led researchers to ask a question. If we intentionally reduce the amount of sunlight reaching parts of the Earth's surface to cool the planet, How might that affect organisms that depend on that sunlight? And the study also showed that changing the sunlight in either case affects photosynthesis. And influencing photosynthesis alters marine productivity. And if marine productivity changes, there are ripple effects throughout the food web. Exactly how large those effects may be and whether it would occur under all real-world conditions, that still needs to be researched. But one reason studies like this are important is it helps scientists identify questions that need answers before anyone should consider deploying any technology. It's a powerful reminder that our atmosphere and oceans are not simply a thermostat we can turn up and down. They're living, interconnected systems, and changing one variable can affect many others. It's probably the biggest lesson we learned from studies like this. When it comes to the Earth's climate, nothing is isolated. Everything is connected to everything else. We live in a very complex planet. Changing even one variable can influence the system in ways we're still working to understand. This research doesn't tell us whether geoengineering is the right or wrong answer. What it does remind us is that every potential solution deserves careful study, because in a system this complex, good intentions don't always guarantee simple outcomes. I'm Dr. Mack, and this has been the Climate Translation. If you have a question about the climate you've been too afraid to ask, or if you have a differing opinion, I want to hear from you. I can use your viewpoints in future episodes. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.